if you're watching this video, I'm assuming you've read this part of the spec, and I'm just going to do a quick little walkthrough of how the A* algorithm works. So I'm going to build myself up towards this figure and go slightly beyond. And how it's going to work is I'm going to talk about from the beginning. So whenever we start our algorithm off, what we're going to do, let's say our initial vertex is stories, or sorry, our initial word is stories, and we want to reach the word shore. So in this case, we will throw stories on the priority queue with a moves count of 0 and a null previous pointer. And this is really just exactly what we saw in the description here, right? So this is that node. Then what we're going to do is remove the node with lowest priority. And if it's the goal node, we're done. Otherwise, then for each neighbor of x, we're going to create a new node that obeys this description, and we'll insert it into our priority queue. So let's see that happen. So we remove stories, so it's gone, and we add all of its neighbors. So in this case, that has only one neighbor in the English language, which is stores. We give it a moves count of 1, and we point prev back here. Okay, good. So next thing we do is we find the smallest thing in the priority queue. It's stores. In this case, then, we will delete that item. So we remove it from the priority queue and add all of its neighbors. So it has 5 neighbors in English, which are stones, store, scores, stored, and stories. Now, there's a critical optimization described in the spec, which is that we do not want to add a node if it's basically its grandparent is itself. So in other words, even though stores does have stories as a neighbor, we don't want to re-add that. Otherwise, we just have this redundant node. It wastes space, could waste time. So in this case, the priority queue is left with 4 items: stones, store, scores, and stored. Now something you might do now to test your understanding of the spec is think about what is going to be the result of the next deletion and why. So I'll let you think about it. Maybe go look at that definition of how the priorities work. Okay, so if we look at all of our particular possibilities, we have, well, it could be stones, store, scores, or stored. All of them have a moves value of 2, but they each have a different estimated distance to goal. So stones, for example, it is got an estimated distance of 3. To get to shore, we would need to change T to H, we would need to change N to R, and we need to drop this S. So that's 3 changes needed. Store, by contrast, it has only 1 change needed, so that's going to be a total of 3. If we think about the estimated distance plus distance so far, and each of these are going to be 2, assuming that I didn't mess it up, so that should be a total of 4. Okay. So scores, I guess let's just go through it. To turn scores into shore, we would change the C into an H, and we drop the S. Same deal here. We take the T, turn it into an H, drop the D. So these should be fine. So at that point, then the next one we're going to remove will be this one right here, because we're deciding which ones are lowest priority based on the sum of this value and the estimated distance to the goal. So at that point, we remove store, which is the lowest priority item. That leaves us with 3 things in the priority queue. And then what we'll do is add all of its neighbors, which happen to be shore, score, story, stone, storm, stored, and stores. However, as before, the word stores is actually its grandparent, so we won't add it back. Now, in this case, what our priority queue ends up having is 1, 2, 3, 4, 5, 6, 7, 8, 9 search nodes, 3 of which have a moves value of 2 so far, and the other will have a value of 3. Now, some of you may note that stored is on the priority queue twice, and some of you don't like that. And what you could do is add an optimization to make sure that you never have a duplicate word. You could do that in many different ways. You can try it out. It might be faster. Maybe try and see if that's useful, though it's not required for the autograder, and depending on how you implement it, it might actually make your code a lot slower. So that's basically the idea behind this algorithm. I hope this is useful, and that's basically that. And exercise for the reader, figure out what's going to be next, but I won't do it in this video. Okay, that's it. So good luck.